Hello, everyone, one more time, and welcome to our SPEC Toolbox webinar series. We are super happy to see you here. Today, we will be covering the topic of Dowel Design of Timber Buildings. My name is Milica Gramusha, and I am a part of the marketing team of SPEC Toolbox. Today, also with us, we will have Bezavit Mezania, who will be presenting today's topic. And then at the end, we will finish, Marko Dimitrijevic, our product manager, will finish up with the Q&A and then some updates that are coming, some updates from SPEC Toolbox team that you will be seeing in the app shortly. So a little bit about Beza, who will be sharing more on Dowel Design of Timber Buildings in a bit. She's been with SPEC Toolbox for the past 3 years, and she's leading all of the connections calculators in SPEC Toolbox team. Prior to this, she's been working as a lecturer in structural engineering, and she's finished a bachelor's degree at structural engineering as well as the master's degree. But she will tell you more about it in a little bit. Just to go over today's presentation. So just give me one sec to. There we go. Oh, this is not. Give me one sec. For some reason, I can't pass it to. I will stop sharing for bring back. And I will share again. Sorry for this team. This always happens when you start presenting. So today's agenda is next. I will give just a short introduction into SPEC Toolbox for everyone who is new to SPEC Toolbox. After that, we will go through the latest updates that are live in SPEC Toolbox app, and then Beza will take us off on the topic of advanced dowel and bolt design for timber structures. And then, as I mentioned, Marko will cover all of the questions that you all have. So next, and this is again not working. I really don't know why. There we go. So we are SPEC Toolbox team, and it's really amazing to see you all. Our mission, as you all know, or some of you know, is to make innovation products easy to specify. And the way we do it is by building a software for the design of mass timber, EWP, and then connection products. We are a team of structural and software engineers, and our teams are based in Indonesia, Ethiopia, Australia, and Serbia. And we are quite, as you can all hear, our team is quite diverse, which we are really proud of. Also, our softwares are, as you can see on the next page, we started in Australia, and now we are working in all different regions of Australia, Europe, and then North America. So since 2023, when we launched the app in Australia, in 2024, we launched the beta program for Europe. And then afterwards, in 2025, we were live in Europe, launched the beta program in North America, and then now we are live in North America as well. So also very proud that our app is being used pretty much all across the world now. This is our global supply partnership and all of the companies that we are working with. It's now since the February 2026, there is quite a few of really amazing companies that we've been working with, and we are very proud of that too. And it's definitely growing. Since February 2026, I'm pretty sure that we have a few more new partners that we didn't have time to put on the map. So it's quite amazing seeing the progress that our team has been making in the past few years. A little bit on our latest release. So we will be talking more into details about the latest release in SPEC Toolbox app on the Dowels module. But besides that, we also launched a new steel plate module And then the screw module got a latest update, and there is also more updates coming in very soon to the app that Marco will be covering at the end of the webinar. And then a really exciting thing that we did this past month is that if you go to our website, you can try all of our calculators on the website for free without logging in and without everything. So the only thing that you need to do is go to the website, try out the calculators. If you want to save any progress, you log into the app and then save it. But we are really trying to make this as easy as possible for people to work in the app, and we think that this is like a massive progress that we made to make that possible. And not to go more into details on all of this, you can definitely follow us, follow our progress, and we are always sharing on our social media channels all of the things that we're working on. So follow us if you want to know more, but I'm going to pass it on to Beza to kick us off with the webinar and our main topic.
Okay. Thank you so much, Melissa, for the wonderful introduction. Let me share my screen. Okay. Can you see my screen? Okay,
Yeah.
thank you. Melissa side, I am Beza Mazenke. I'm currently the lead structural engineer and connection lead here at SPEC Toolbox. So in today's webinar, we will be covering designing with Dowels in comparison with the Eurocodes, the two Eurocodes, Eurocode 5 2004 and Eurocode 5 2025. Thank you all for coming. So before starting, I'd like to give a special thanks to our senior structural engineer, Theodros Mamu, who have been doing this, the Dowel calculator for the past months. So on today's session, we'll be covering the Dowel Design Theory in comparison with the two codes, Eurocode 5 2004 and Eurocode 5 2025. We will also see a simple connection, bracing connection detail, and also we'll see a moment resisting connection detail, and we will try to compare the capacities using our software with the two codes. So let's go straight to the theoretical part. So let's start with what Dowel type fasteners are. So when we say Dowel type fasteners, we are referring to nails, screws, staples, dowels, and bolts. But in this is a webinar, we will be specifically looking at dowels and bolts. So in these types of fasteners, when we have a shear load, a load perpendicular to the fastener axis, this load will be resisted by a dowel action. So this will include embedment on the timber member as well as yielding failure on the fastener. So there are some parameters that affect the capacity of the system. So the first one is the yielding strength of the fastener. So this is given by this formula. As you can see, this again depends on the diameter of fastener and the strength of the fastener. We'll have also another parameter, that's the embedment strength of timber. So this is given by this formula. This is slightly different in the two codes, but it's more or less the same. We have this top part, and then we have a modification factor for material and load angle. So in this formula, you can see that we have the rho K, which is the characteristic density of the timber. So this depends based on the timber material. We also have the K mod factor. So this depends on the load and K-mat, yeah, this depends on again the type of timber material. We have a K90 factor embedded inside this. So K90 varies from if whether our timber member is JLT, LVL, or ST, and also have an angle adjustment factor. So as you can see in this picture, if we have a load parallel to the grain direction of the timber, this has a different capacity that if we have a load and in this direction, or if we have a load perpendicular to the grain direction, we'll have another capacity. So this will be incorporated into the K-mat factor. The next one is the rope effect. So the rope effect will only be applicable for bolts, and for dowels we will have a zero rope effect. So what rope effect is, let's say if we have a lateral load, as you can see in this picture, this load will tend to elongate the fastener, but this elongation will be resisted by the heads of the fasteners, and this would have a clamping effect on the overall system, and this clamping effect will increase the lateral load carrying capacity. So this is basically the withdrawal strength of the fastener, but we will not directly take the withdrawal strings, rather we take 1/4 of the withdrawal strings. But again, this 1/4 of the withdrawal strings should not be greater than the 0.5 or still 1/4 of the Dowel effect part. The next one is the thickness of the member. It has also a significant effect on the characteristic load bearing capacity. And another parameter is the diameter of the fastener, and also the number of shear plates have a significant effect on the Dowel effect contribution. So once we set this, next we will see the yield failure equations in comparison with the two codes. Here we have the first one is for Euro code 5, 2004. So for this code, for a single shear fasteners, single shear steel to plate connections, we have 5 different failure modes: 2 failure modes for thin steel plates and 3 failure modes for thick steel plates. So we classify thin plate and thick plate based on the thickness of the plate in comparison with the diameter of the fastener. So if the thickness of the plate is less than half of the diameter of the fastener, we classify it as thin plate. And if the thickness of the plate is greater than the diameter of the fastener, we classify it as thick plate. For those values of the thickness of the plate in between thick and thin, we interpolate the results. So for thin plate, we have 2 failure modes, and for thick plate, we have 3 failure modes, as you can see. When we come to the new code, Euro code 5, we have 6 general failure modes. So these failure modes will be applicable both for timber to timber and steel to timber connections. And we have these failure modes without any classification between thin and thick. We just proceed with this calculation. So as you can see here on the top 2, we have an embedment failure mode. So on the first equation, we have embedment failure in the first member, and on the second equation, we have embedment failure on the second member, and on the third one, we have embedment failure in both members. And for the failure modes below, we have a combination of embedment failure as well as fastener yielding. So the next is for double shear connections. For double shear steel to timber connection, again for Euro code 5 2004, we have different provisions for steel with steel connections and for with steel with connections. For steel with steel connections, again we have different provisions for thin steel timbers and for thin steel plates and for thick steel plates. For with steel with connection, we have 3 failure modes again. When you come to the new code, we have 4 generalized failure modes selected from the 6 equations we saw for single shear fasteners. So we have the same equations for steel with steel as well as for with steel with connections, but the difference is slightly on the applicability. So for steel with steel connections, we take the member 1, or if the embedment failure 1 would be embedment failure in the steel. But when we come to the wood steel wood connections, embedment failure 1 would be embedment failure on the timber member. So when we if you have steel wood steel connections, FH1 will be embedment failure of the steel in all of the equations. And when we have wood steel wood connections, FH1 will be the embedment failure of the embedment strings of the wood member, and we will take that in all of the equations that follows. So far we have seen single shear and double shear connections. What about multiple shear connections? So multiple shear plane connections, on the two courses, we have the same approach. So what we take is, firstly, we divide the multiple shear plane connections into a series of double shear connections, but we have to make sure that these double shear connections have to be compatible to each other to sum up the final capacities. So failure modes A and B These modes are, as we have seen, impairment failure in one of the members. So these failure modes shall not be combined with the other failure modes that have fastener yielding. So we should not combine this. Other than that, we just add the double shear connection capacities to get the multiple shear capacity. So to sum up, Euro Code 5 2004, for a single shear plane connection, we have 5 failure modes, 2 for thin steel plate and 3 for thick steel plate. On the new code, we have 6 general failure modes. For double shear connections, we have for steel with steel and for wood steel wood, different equations on the Euro Code 5 2004, whereas we have 4 general failure modes on the new code. For multiple shear connections, we take a series of compatible double shear connections in both cases. So this is all about single shear, double shear, and multiple shear connections in comparison with the two codes. Now let's move on to a system of the connection when we have a moment or when we are just doing a simple connections without any moment. So for simple connections without any applied moment, or we can take a simple bracing system. What we do is all fasteners will have the same load share. So the load applied will be equally resisted by all fasteners. So for this assumption to be true, we are assuming that the load is applied on the centroid of the bolt group or the fastener group. So if that's satisfied, we will have all fasteners with the same load carrying capacity, and also all fasteners will have the same load share. The total capacity would be single fastener capacity multiplied by the total number of fasteners, but we will have to consider the effective number of fasteners. So effective number will be multiplied by a single fastener capacity to get the total capacity, and we have the total applied system load, so we get the utilization. When we come to moment resisting systems, since due to the applied moment, all fasteners will not have the same load shares. So on our calculator, we followed a rigid system, a rigid model approach. So on this approach, what we assume is all fasteners or all connectors will rotate at the same angle with respect to the centroid of the bolt group. The fastener with the farthest distance from the center of the bolt group will have the higher deformation, as well as this fastener will have the highest load share. So this will be calculated based on a simple statics for the shear in axial force or for the lateral loads in the different directions. We take the load share will be the applied loads divided by the number of fasteners, but whereas for the moment, the load share will be considering the distance from the centroid of the bolt group or the fastener group. So, as we said, force on each fastener is different. Since the force is different, the angle between the force and the grain direction on each fastener will also be different. So, as you can see, due to the applied moment, the force on each fastener, both the magnitude and also the angle is different. So, due to this, we will have a different angle between the load and the grain direction will be different in each fastener. So since the load angle affects the characteristic load carrying capacity, the characteristic load carrying capacity of each fastener will also be different. So while doing the utilization, we have to consider both the applied load as well as the resistance. So there will be a governing fastener. So this fastener is most of the time the fastener at the farthest location from the center of the bolt group. So to summarize, for a simple connection, we do the capacity per fastener, and then we multiply by effective number of fasteners to get the total capacity, and we have the total applied load, and then we will do the utilization. When we come to the moment resisting connection, we have to select the governing fastener. So capacity of the governing fastener will be computed, and then we multiply by the effective number coefficient to get the total capacity. The load will also be different from fastener to fastener. So we will take the applied load of the load share on the governing fastener. So we do the utilization for the governing fastener. So this was all about uh, the lateral load carrying capacity of the fastener group. But on the Eurocode, in addition to the characteristic load carrying capacity using the European yield model equations, we also have to check, in order to say we have done a full design, we also have to check the minimum spacing requirements, as well as the timber might also fail in brittle failure modes. Those also have to be considered. So let's go to the minimum spacing requirements. So these have to be requirements, have to be satisfied, so that our calculated capacities are achieved. So for this, we have five types of checks. We have check for spacing parallel to the grain, spacing perpendicular to the grain. We have loaded in the distance, and we have unloaded in the distance. We have loaded edge distance as well as unloaded edge distance. So let's compare the minimum requirements given on the two codes. These are more or less similar, but the new code being more conservative. So as you can see here, we have cosine of alpha, where alpha is the load angle, as you can see. So this will be maximum when you have load parallel to grain, or when the cosine is 1. So this will be equal to the one given on the new code. Other than the cases where the load angle is not 0, we have more conservative results on the new code. So as you can see, most of the others are almost the same. Again, here we have more conservative results on the new code. So the next is the brittle failure modes. So these also have to be checked in order to say we have done a full design. So for the new Euro code, we have some brittle failure modes. So for load parallel to grain, for the applied load parallel to grain, we have some checks. For if we have only one row fastener, we check these three checks. We have the row shear resistance, and we have the splitting resistance. Due to the load, the fastener group might split the timber. We have the netting side resistance as well. If we have more than one row fastener, we have to check these three checks. In addition, we also have block shear resistance and plug shear resistance. So for fasteners fully penetrating, we check the plug shear resistance, but for fasteners partially penetrating, we check the block shear resistance. We have the same checks, some of the checks on the old code, on the Euro Code 5 2004. We have the block shear resistance as well as the plug shear resistance. So this was the previous was for load parallel to grain, but for loads perpendicular to grain, we have splitting checks. So this checks is found on both codes. So for load perpendicular to the grain, this load might split our timber member. So this also have to be taken into consideration. So this was all about the theoretical part. Now let's go to specific design examples using our software. Okay, so here we have a vertical bracing design. We have a wind load and also a gravity load. So this analysis has to be done on another software, and we take this analysis results for the both wind load and for gravity load. So the maximum is on the ground floor. So here we have a maximum tension load of 68.3 kilonewton and maximum compression load on the bracing systems of 175. So we'll design this on our software. So since we have a wind load combination, we take the K mode of 0.9 on our calculations. So for starting, let's do a timber member of 180 millimeter by 260 millimeter and GL30 H timber, and with bolts M15 and M12. Okay. Okay. So, sorry for that. When you open our software, you will get when you log in onto our software, you will get this window. So here we have you can get the Dowel or Bolt design. So here you can create your own project and then proceed. So for now, let's just I have saved calculators. Let's go to those. We have for the first one we have a bracing beam connection example. So let's do for the compression load of 175. Let's change the input to minus 175. This is the force input. Uh, so we take the JL30H and with a timber thickness of 180 by 260. So I have used manual grade inputs, but you can also, if you want to do different suppliers, we have different timber suppliers. You can choose from what you want. So here we set our
Yeah.
inputs.
There's just one question. I think the screen is frozen.
Oh, okay, let me share again.
That's it.
It's working. Okay. Okay, sorry for that. I have already inputted the load in the timber cross sections. So as I mentioned earlier, you can have different timber suppliers chosen from this. For now, I have I'm going with manual input of grades. So we also have different grade options to choose from. I have JL30H and I set the initial thickness to be 180 by 260. So you can also see the dimensions change from this. We have a 3D plot as well as 2D plots if you want to look into the details. So I have chosen a double shear plane or two steel plates. You can also change this one as you like. So this is the loading on the design methodologies. We have the two code options, so we can play with this as well. Uh, so we have the member data here. We have the steel plate data here. So these are you can change this one as you like. So we'll do the optimization later. We will change inputs based on the output. So here we have the fastener data tab. So you can change between bolts or darts. You can choose the fastener grades. You can choose the bolt diameter. You can choose the bolt distribution. Maybe if anything is unclear, you can always look into the more information of our calculators. So here we have three options: even, uneven, and uneven one and uneven two. So you can always look into the more information. As I mentioned, we have an even distribution of bolt groups here. We have an uneven distribution like this or an uneven two distribution like this. So you can choose from whatever you want. We can also change the number of rows and number of fasteners per row as you want. So let's go with the default and look at the output, and we will do the optimization later. So for the spacing and edge distance requirements, we have again different options. If you want to automatically take the minimum criteria from the code, for edge distance, you can do minimum edge distance, or if you want the spacings to be minimum values, you can do minimum spacing. You can also do a user-defined edge distance and user-defined spacing criteria. So for this example, I will be going with the minimum edge distance criteria. Here we have 37.8 percentage. So as you can see, 37 is underutilized. So let's change our fasteners so that we have a good utilization. Okay, so since we have 37, let's change the number of bolts. So you can change the numbers here, and you can see the numbers to automatically change on the dynamic plot. So we had 5, let's reduce that to 3. So here we have 3 by 3 fasteners. For the number of rows, let's do 2 rows. So let's make 2 by 3, and let's go with an M team. So we have 89% utilization, so I think that's okay. We can also check that by changing the code. So we have 72% on the yielding, and for the splitting we have 86%. So I think this is okay. We can proceed with this one. Let's look into the detailed calculations. So for the geometry check, we check the timber member as well as the steel plate. So you can change here and see. For the timber member, we have spacing requirements as well as end edge distance requirements. For the steel plate as well, we have those requirements. So if anything is unacceptable here, you can go back to the input section and change as you like. We also have the stiffness calculations, and we have the design parameter calculations. We have the timber density, shear strength, tensile. So this is selected from the grade chosen. And here we have the calculations to proceed. And let's go to the next tab. We have the yielding resistance tab. So here we have embedment strengths on the steel plate as well as on the timber member. So we do. We also have the rope effect, as well as after the rope effect, we go to the embedment strengths equations. So as I mentioned earlier, we have 4 equations for steel. This is the new code. I chose the new code. So for the new code, we have 4 equations for steel with steel, and we have again 4 equations for with steel with connections. So since we have multiple shear planes, we change the multiple shear plane into a series of double shear connections, and then we do a compatible failure mode. So for the compatible failure modes, as I mentioned earlier, failure mode A and B shall not be mixed with the other failure modes. So these are all the possible combinations. So from these possible combinations, we select the minimum one, and then we add the rope effect, and then we calculate the effective number of fasteners, and we have this utilization. We also have checked the steel plate. Okay, before that, let's go to the brittle failure mode tab. So we have parallel to grade loading. So we have these modes for parallel to grade loading. We also have the timber cross-section check for the compression loading, and we have the steel plate tab for the compression capacity. So this is for the negative force. Let's go with the 63 kilonewton tension force. So for this one, since most of the calculations are the same, I'll just go with the main differences on the brittle failure modes. So I will go to those. So for the new code, we have a lot of brittle failure checks. So for a parallel to grade loading of tension loading, we have row shear resistance, and then next we have block shear resistance, as well as net tensile resistance. So in splitting parallel to grade checks, you can always look into the detail tabs here. So this is all for the bracing example. Let's do another example. Okay, let me go to the PowerPoint. Okay. So this was all about the vertical bracing example. Let's go to a moment connection design. So for this example, we have category B, floor spanning 5 meter with 6 meter. We have a live load of 3 kilonewton per meter square and a dead load of 2 kilonewton per meter square. So for this load combination, we have 10.5 kilonewton per meter square loading, and for this loading, we have a 78.78 kilonewton force on the beam, and we will transfer this load later into the column, and then we will do the design of both the beam and the column. So for the beam, let's do the beam part first. So for starting, let's also take the dimensions of 180 millimeter by 260 millimeter JL30H with 15 bolts and M15 bolts with 12 millimeter diameter bolts with a double steel plate. So let's go to our software now and let's design this. Okay. So here we have the beam example. So as we saw on the analysis, from the analysis results, we have 79 kilonewton shear force. So we can always look into the dynamic plot on the loading. Let's take 180 by 260 for starting. So we'll play with the codes later. We have the member and the steel plate data. As I mentioned, we can always change these inputs. We can also change the fasteners. So for now, I have set to 15 fasteners, 3 number of rows, and 5 fasteners per row, and 12 millimeter bolts. So let's go to the output. We have a yielding resistance of 23% and splitting resistance of 173.5%. So both of these are not optimized. Let's do the optimization. So for the splitting, let's go to the splitting tab. This is under the brittle failure tab, and let's look into what we can change to increase our utilization. So here we have this formula. We have chosen Eurocode 5 2004. So for this code, we have this formula. We have the B, that's the timber thickness. We have the modification factor, and we have HE, which is the loaded edge distance. So this is the distance from the farthest fastener to the loaded edge. So here, since I have chosen the minimum edge distance criteria, this is the minimum that we can have here. So to increase our capacity, our only option will be to increase the width of the timber and increase the height. Because if we increase the height, we can increase the HE or the loaded edge distance. So let's change this to 200 or 220. We can always check the utilization and update our inputs. Let's go with 320 millimeter tapes, and let's see our utilization. So I have decreased the splitting strength a bit, but still this is not okay. So let's do another optimization. We can optimize this by decreasing the bolt diameter, because if we decrease the bolt diameter, we can decrease the edge distance. So if we have 12, we had 48, because the criteria depends on the bolt diameter. So let's go with this and let's check. So yeah, now our splitting is well optimized, but the yielding is a bit low. Let's we can decrease the number of fasteners for this. Let's do 2 number of rows. Now we can proceed with this one. This is okay. So the splitting resistance has a bit update on the new code. So let's see the checks on the new code. So previously we only had if you remember, we had a 14 coefficient here on the old code. So we had 14 here, and then the other parameters are already included on the new code as well. So on the new code, we have different factors that take into consideration the different parameters. But on the old code, this was summarized with 14. So this is a bit more conservative. As you remember, we had 80 something utilization on the old code, but here we have 47% utilization because of these factors take into consideration each and every parameter that affects the splitting capacity. So this will be enough for our beam example. Let's go to the column example. Okay, let me share my screen. Okay. So for the column example, what we are doing is we are transferring the load from the beam to the column. So we will have a moment arm. This moment arm will be from the center of the fastener group of the beam to the center of the fastener group of the column. So we have here, if you remember, we took two columns of fasteners. So we will have spacing over 2 here, and we have the edge distance here, and then we have the column dimension over 2 here. So we'll have 218 millimeter moment arm, and we have 79 kilonewton force. So we'll have 17 kilonewton meter moment. Since we set the timber thickness of the beam to 220, let's take 220 for the column also to align with the beam. Let's take 220 by 220, JL30H, 15 bolts with M12 diameter. Let's go into our design, and we will do the optimization based on the design results. Okay. So I have already set the inputs here. We have JL30 timber. We have 220 by 220. So we have 79 kilonewton. It's now tension load for the column, and we have 17 kilonewton meter moment. So let's have 3 number of rows and number of fastener per row of 5. We will do the output summary, and we will do the optimization. So here I think we have all results to be okay. We will do our optimization later by changing one of the parameters as we like. Let's go to the different parts of the calculations. Since we have already seen the geometry check, it's the same with what we had earlier. I think this tab is a bit different for the moment resisting systems. So as we mentioned, the fastener group will rotate with respect to the bolt centroid. So the load share by each fastener will be different. We have here different parameters that affect our calculations. You can see that. So we have the resultant force of the governing fastener here. You can also see the loads resisted by each fastener. So let's go to the next tab. We have the fastener IDs here. So for each fastener, we have the load shares here. So the green highlight is the one with the higher load share, or the governing fastener. So you can also see the resultant force per fastener, and also the load share due to each applied force. Since now we don't have any vertical shear, we have 0 here, and here we have the load share due to the horizontal shear force. So once we have this load, our calculations will be the same as the previous one. We have the rope effect calculations here, and then the impediment strength calculations, both for steel wood steel and wood steel wood. and then we will do the compatible failure modes, and then we will add, and then we will take the minimum capacity, the minimum value of the failure mode. So here we have 54.3 of capacity of the minimum or the governing failure mode. So we'll take this one, and then we will do our calculations. So we have a 40% utilization. So this is, the other tabs are the same. Let's do some optimization for this design example, and we will end our example. So if we change to number of fasteners to 3, I think we have 90% utilization. So this is okay. Okay, let's go back to our PowerPoint. Okay. So to summarize, if we want to do some design optimization based on spacing and distance requirements, so this has some effect or a bit different effect on moment resisting systems and simple bracing systems. So if we have minimum spacing, or if we do small spacing, we will affect our brittle failure, or our timber member will be prone to brittle failures. And that's right. Okay, we will share again. Okay, can you see my PowerPoint now?
Not yet.
Not yet. Okay. I'm not sure why it is not sharing, but this is a small portion. I can proceed to PowerPoint. Okay. So for spacing, if we have a minimum spacing, we will affect the brittle failures, or we would make our timber more prone to the brittle failure, because we will have a smaller area. As you can see, as you can remember, especially for row shear resistance, if we take that example, if we have a smaller spacing, we will have a smaller circumference to resist the applied load, so that our timber will have a smaller capacity. But if you have a larger spacing, what we have is the effective number calculations are dependent on spacing. So if we have a higher spacing, we will have a higher effective number, and this will increase our overall capacity. And for moment resisting systems, if we have a smaller spacing, we will have the governing fastener will have a smaller load arm, so we will have a smaller load share due to the moment. And also the other parameter is the number of shear planes. So if we have a smaller number of shear planes, we will have a higher thickness for individual members. And if we have a higher number of shear planes, we have a higher number of compatible failure modes, and we can add those. So for the number of shear planes, we don't have a direct effect. So we have to change and see for ourselves the differences. So my next slide was on the calculator next versions. So for now, we only had one member calculation. But for next versions, we are planning to have different members connected into one system, and we will do a design of all members. So this is all from my side. Over to you, Marco.
Thank you, Beza. That was incredible. hope you everyone enjoyed. I saw we have a few questions we will cover out. Before we go straight over to the questions, I'll just share my screen quickly to give you some of the information about our next releases. So I'll just share my screen right now. So here we go. For everyone who are first time with us now, if you are keen to check out more and especially get all the functionalities and features, you have option for 60 days free trial if you reach out to us. So you just need to register using this link and reach out to us, and we'll provide you the full access straight away. Just a preview also on some of the functionalities and optionalities. So most of the calculations are free, but if you want to explore manual input, some of the customization options, and also enterprise functionalities, that's something that is only available to pro and enterprise customers. So once again, anyone who wants to explore this, feel free to reach out or leave your contacts in the chat. In terms of the upcoming updates and what we're currently working on, so something that you will see in the app basically in the next couple of weeks. First, we're working on the panel connection updates. So we are rebuilding our connection details, and this is first batch of new connection details will be launched in the app. So this includes half lap, spline, and butt joint. So including new functionalities rebuilt to the latest version of Eurocode 5 from 2025 version, and also including all functionalities and ETAs from all of our suppliers that we are already working on. Also, one major update. So as you already all saw what the Beza presented for the large Dowel bolt calculations, we are working on the new UI and UX interface. So this is just a preview of how this will work and in what direction we are going. So practically, we are listening to your feedback, and every time we try to improve what we're doing. So this is the case where all the inputs and outputs will be redefined, and you can easily find all the things, checks, verifications, and sections, as well as the preview image will be always on the screen. So some of these things we are finalizing and will be in the app very soon. Also, what we are working something this in particular for as a lot of requests from you were around fire design. So as you know, currently we have a limitation where non-fire and fire design are two separate calculators. We finally combined that into the one single module that will be available soon, and also we updated the 2025 version of the new Eurocode as well. So anytime you're in the regular CLT floor calculator, you will have an option for just adding fire calculation to it. So all the inputs will be taken from original design. And going further, also one big improvement is a new CLT shareable. So this is something that we are been working for a while. So some of the updates in terms of the dynamic plots, brackets, and hold downs will be directly available, and we'll have multiple floor level calculations. So just a preview of some of the updates. So as I mentioned, you can contact us through the website, to the admin login, or to with my email, and we'll provide you with all the information, answers, and we can give you pro access as I mentioned. We can quickly go through to the questions now. So we have plenty of these things to be addressed. So firstly, we have a question that is it possible to export a PDF from the Dowel calculator? Yes, it is. So as basically from all of the calculators we have, that's something that you can use. Not sure, Beza, if it's something handy on you and you would like to share that, but if not, we can go further to other questions. We have one more question here in the chat. So we have a question that if the internal steel plates can be arranged symmetrically, or there's option to place them exactly where we want. Beza, do you want maybe to explain this? or never mind, I can also answer. So in terms of the internal plates, so currently we don't have an option for manual placement. It's only symmetrically, but we're working on the next batch of updates where this will be available. Going.
Okay, Marco, thank you maybe for the symmetrical steel plates.
Yep.
Yeah, we are currently working on that. We have now we have on the uniform arrangements, but we are working on non-uniform arrangements as well as circular bolt distributions will also be in future updates. I think there is also a question on shorter dowels. That's also on our list of things to be on future update.
Perfect. Thanks so much, Beza. And there is also actually two more questions. So, is there a link with static software like Global RFM 5? I believe this is probably meant to be like interoperability, or there will be connection with software like Global RFM 5. Maybe I can take that. So at the moment, we don't have the option to connect with Global or any other software, but we are working on providing the API and connectivity with such a software. So it will be much easier to do the global design and such a software, and then local verification in our modules and calculations. So yeah, thanks for that. And maybe one more thing is any thoughts on designing this type of connection in seismic regions, and especially according to New Eurocode 8. So not sure, Bez, if you have any thoughts on this.
Yeah, so currently we are still on our, this is still on our list. But what Eurocode recommends is we have overstrings factors and understrings factors based on ductility classes. So we'll have overstrings factors for brittle failure modes, because especially on seismic regions, we don't want the brittle failures to happen. So we make sure that those don't happen using overstrings factors, and we have understrings factors for yield model equations. So we have the failure modes. From those failure modes, we should only allow the failure modes with ductile failure, especially modes that require yielding of the fasteners. To do this, we can have more slender fasteners or longer fasteners with smaller diameters, so that this failure mode will happen before all the other failure modes. So this is also on our list.
Thank you, Beza. Yeah, I think we covered most of the questions. If anyone else had any questions, thoughts, or comments, feel free to write us anytime. Also, feel free to explore the calculator Beza shared today. Also, any others, and feel free to let us know if you have any feedbacks. We strongly recommend to ask any questions and any thoughts, so we can provide you explanation, but also improve. And I think that will be all for today. So thank you everyone for joining us, and see you next month with our next topic regarding CLT shear walls. So once again, thank you Beza, thank you Melitza, and thank you everyone.
Thank you, everyone.
Bye.